All right, in this chapter, we're starting a totally new topic. It's Introduction to Logic. In fact, it's formal logic. Our first section is referred to as statements and quantifiers. Let me go ahead and give a definition first. Definition. A statement is a declarative sentence that is either true or false. Examples of such statements: we have a cell phone is a way to keep in touch. This is a true statement. So these statements have to be either true or false. They have a numerical value, if you will, of 1 if it's true, 0 if it's false. So for every sentence we can do something like that with it. For example, this is a perfectly good statement. In fact, it is a sentence, and it's a true sentence. On the other hand, while that sentence right there declares something, it is a false statement. All right, this example, I have a collection of sentences, and we're going to decide whether they are statements or not. So take a look at number 6. I pulled these right from the book. The zip code for Oscar, Louisiana is 70762. It doesn't matter if it is actually that or not. It could be a false statement. That's not a problem. The fact is, it is a sentence, and it is making a declaration that something is true. So its value is either true or false. So this is indeed a statement. Moving on. Number 8. Did you silence your cell phone? Now that's a question. That's not making a declaration. So if I change this to you silenced your cell phone, then it would be a statement. But as it is right now, it is not. Equations are automatically statements because they're either going to be true or false. Number 12, it is making it once again a declarative statement. It is saying that somebody was president. Whether it's true or false is irrelevant to this question. It is in fact a statement. Let me pull 14 up here. So it's projected. That means that something is being declared. So it is a statement. Once again, whether it's true or false does not matter. The fact that it was projected means that that statement either is true or false. Behave yourself and sit down. That is not making any kind of a declaration. That is a command. So this is a no. Next, we complicate things by throwing in the notion of a negation. That's where we take the opposite of a statement, essentially. The negation of a true statement is false, and vice versa. The negation of a false statement is true. So how do we do a negation? Well, let's do an example. The sky is blue. That's clearly going to be a true or false statement. So what is the negation? So the negation is the sky is not blue. So that's the negation of that statement. The pen is not red. The negation is the pen is red. So write the negation of the statement that I'm about to give. The trash needs to be collected. This seems pretty clear. The trash does not need to be collected. Or maybe I'll call it solution. No rain fell in Southern California today. We simply would write rain fell in Southern California today. All right, this is a different kind of problem here. When we think of all students, we want to think of the negation of that as none, and that's not true. The negation of all is at least one of. So if I say all students will do something, the negation of that is at least one student will not do something. So let me write it. At least one student present will not get another chance. Some people have all the luck. So the negation of this is that no people have all the luck. Now mathematically, we also have statements that we can look at, true or false statements. Consider the statement x is less than 10. You probably did this, but if you drew it on a number line, what you would do is put this little hole where 10 was, and then typically do some sort of a shading. Once again, the negation, you have to be careful. The negation wants to make all of these not solid anymore. That means it's going to do the exact, I don't know if I want to say opposite, but it is the exact opposite. It's going to fill in these, and it's going to include 10. So the negation is actually x is greater than or equal to 10. Notice if I were to write this as a number line, it might help you to view it this way. Let me put my circle again. But this time it's going to be filled in, and I'm going to shade the other side. Hopefully you can see when you put those two together, you get the whole real line. So if you have something like x is less than -6, the negation is x is greater than or equal to -6. If you have x is greater than 19, the negation is x is less than or equal to 19. And of course, if you have something like x is less than or equal to -20, the negation is x is greater than -20. Now this is where we get symbolic. We're going to typically use letters to represent statements. making sort of an algebra behind it. So I might do something like this. P might equal the following statement. She has green eyes. Or maybe Q, he is 60 years old. And then we would do a squiggle P if we want the negation of P. So this will equal she does not have green eyes. Or the negation of Q equals he is not 60 years old. Other symbols. So just remember, the squiggle means negation. We have other symbols that we use. For example, we have a V shape, which means the word or. And then we have an upside down V shape, which means the word and. Remember, or has the same feeling and meaning as we used when we were doing the union, and has the same meaning and feeling as when we were doing intersections. So keep that in mind as we go through these problems. All right, let's do some more things with these. What this allows us to do is build more complicated statements. So we just did squiggle Q. That was he is not 60 years old. I'm going to drop the quotes from now on. Now P, V, Q, this should be P or Q, means this is the statement we'll use. She has green eyes, or that's the V. He is 60 years old. There's your compound statement. Here, P and not Q, we have she has green eyes and he is not 60 years old. Not P and not Q. We have she doesn't have green eyes and he is not 60 years old. And then look at this thing. Now this is weird. You can do this if you want. Let me do the stuff inside of the parentheses first. So here's what I have. She has green eyes, or he is not 60 years old. All right, that was the stuff that was inside of the parentheses. And now I have to do the negation of all this. So I basically have a negation of this whole thing. So how do we do that? Well, we change an or to an and we do the negation of each thing inside. So basically the way this works, let me write this here. There's an equation involving this, and this equals not P and regular Q. So let's take a look and see what that version of it looks like. She does not have green eyes and he is 60 years old. Now let's take a look at if that really makes sense. Is that the negation of what was it? She has green eyes, or he is not 60 years old. It might be easiest to think of this not in regards to what I just wrote down here, but let's take it easier. Let's move out of this for a second, and it seems more complicated. So if we have P or Q, I want to know what the negation of it is. So I do negation P or Q. Let's take a look. Consider what we have when we do the negation of P or Q. When I look at P or Q, either P is true or Q is true, or maybe both of them is true. Now, what does it mean to be the negation of that? Well, the negation of that means that we started with either one or the other was true, or both, and now we want both of them not to be true. So if you're saying the opposite of one or the other thing being true, the negation of it is that both of them are not true. So the negation of a statement where one or the other or both are possibly true is the opposite of each one, but now it's changed to an and. So you need to be careful of that. I believe this is referred to as one of De Morgan's laws. I don't care about the name of it, just so that you know how to use it. It's hard for me to come up without using symbols how this applies to the statement I was just looking at right here. How do I negate that? Well, the only way I know to negate that is to use the symbol equation that I have here. That means that I'm going to negate the she has green eyes, so that's where I have this. And there's that part. See how it changed to an and? He is not 60 years old. The negation of that is he is 60 years old. And we also have another one. If I should do this, this is going to be squiggle P, V, squiggle Q. So these two rules are very useful in this type of logic, which is referred to as symbolic logic. All right, here we're given a problem where they want us to convert to symbols, and they have given us phrases. So P is going to be the part where Tyler collects DVDs, and then Q is Josh is an art major. So we want to take these compound statements and convert them to using P's and Q's and other symbols. So let's take a look at what we have. Tyler does not collect DVDs, so that part right there is not P. And then we have a V, and then Josh is not an art major, squiggle Q. So that'll be squiggle P, V, squiggle Q. Number 52, Josh is an art major. Well, there's our and. Let me get that. So that's just P. Tyler does not collect DVDs. Oh, they went and switched them on me. Be careful of that. They've decided to put Josh as an art major first, so that's Q. And Tyler does not collect DVDs. So we have Q and not P. And the last one, either Josh is an art major or Tyler collects DVDs. Let me block that off because that's one chunk. And it is not the case. Okay, so then we have, and it is not the case that both Josh is an art major. So there's a P again. There's P. And Tyler collects DVDs. Oh, they switched it on me again. Let me put my Q first. And then Tyler collects DVDs, so we're going to have P. So what I'm going to have is a compound thing. Here we have an and. It is not the case, so I have and squiggle. It is not the case. So either Josh is an art major or Tyler collects DVDs. So we have P, V, Q, and that. So I would put parentheses around that. So it could look, I guess, well, let me clean it up a little bit. Your book would prefer that you put the squiggle inside of a containing device, like I have. This is not assignment here. This is from the textbook. We have 3 groups. So this would be like group 1. So that's group A, I guess. Let's just call it group A. Group B, and then group C. Refer to the groups of images of mathematicians labeled A, B, and C, and identify by letter the groups or groups that satisfy the given statements involving quantifiers. So let's take a look. Number 58 says no picture has a frame. Are there any of these in which this one has a frame there, this one has a frame there? So that's false. But right here, this one here has no frame for any of the people in there. So for B would be true for that statement. Now 60, not every picture has a frame. That would be A and B. Not every picture does include the possibility of none of them happening. No picture does not have a frame. So this is interesting here. Think about this. None of the pictures do not have frames. That means all the pictures have frames. That would be C. I want you to keep this in mind. If we do the negation of something, it equals the something itself. 64. Not every picture does not have a frame. Not every picture does not have a frame. So let's start with, forget about this for a minute. I'm just going to exit out. Every picture does not have a frame. What were those that was true for? Every picture does not have a frame. So A, every picture, that would have been true for A. B, every picture does not have a frame. Actually, I was wrong about that first one, wasn't I? The only one that's true for, every picture does not have a frame. The only thing it was true for was B. With that in mind, if I take the not of all of that, that means that the statements that were false, which were A and C, they were false before, now they become true. Next, we're actually going to write up some sets of things that you probably have seen before, but I'm going to reintroduce them. This is where we're going to start getting into some arithmetic. So the natural numbers, we use this weird symbol n, like that, and they start at 1, and they go on forever. The 3 dots indicates that that set goes on forever. And the whole numbers, I have made up my own symbol for it. The book doesn't have this symbol, but I'll use sort of like a weird W like that. It's the same as the natural numbers, except it starts at 0 instead. Then we have the integers. Here they use the letter Z, believe it or not. It's a German word, Zahlen, meaning number. But here the integers have 3 dots at both sides. That's because they contain negative and positive natural numbers, and even 0. Notice, let me throw this in here. This W is the same as the natural numbers with the addition of 0. And of course z is equal to ... -3, -2, -1, 0 union the natural numbers. The rational numbers are a difficult one to write down the set for. But these things are going to look like this. They're going to use Q for quotient. It's going to be all the items that look like this, A over B, such that A and B are integers. Additionally, B cannot equal 0. So examples of rational numbers are simple: 1/2, -2/3, 5/8, -27/4, or 5. I really don't care. Other numbers that you may not think belong in there actually are all the integers. So if I take any integer, say -5, it's the case that -5 is -5/1. Even 0's in there, because 0 can be thought of as 0/1 if you wanted to. And then the set you're probably dealt with most of your life, the real numbers, that's going to be this weird R, and it's going to be all numbers x such that x has a decimal expansion. So anything by now is a real number. All those rational numbers are real numbers, but now you have even more things. Like, so I can take any integer will be in here, like -5. Any rational number will be in there, 1/3. And then numbers that are not anywhere else, like pi, the square root of 2. It goes on. There's all sorts of other numbers, 10, 0's in there. So I can't possibly list even a good collection of them. They're so infinite. All right, my last example, I don't know if I really specified, but a quantifier is something put between or put before something to specify something, if that makes sense. Right here, this word every is the quantifier. This says every single integer is a whole number. Let's take a look back at these sets. There's the set of integers, and there's the set of whole numbers. Is it true that every integer is a whole number? Well, no, that's not true. You can see there are negative integers over here, negative integers that are not in this set. So this is clearly false. There exists an integer that is not a natural number. Once again, this is the quantifier. There exists an integer that is not a natural number. Well, yeah, take any negative integer, and any of those are not natural numbers. So this statement is true. All irrational numbers are real numbers. I did not write this down, but let me use this opportunity to write down a set that goes by cursive I. This is the set of all real numbers, so x is in R, but x is not a rational number. So it is true that all irrational numbers are real numbers. It turns out the irrational numbers, the ones that are inside of there, are things like pi, the square root of 2, things that have infinite decimal expansions, but they're not repeating decimals. They have no rhyme or reason. Well, they may have some patterns to them, but any number where the decimals go on forever and are not repeating is known as an irrational number. The set of whole numbers are not rational numbers. I believe they are. Remember when I told you that rational numbers contain all the whole numbers, because all you got to do is take any whole number and divide it by 1, and you've made it into a fraction. So that, actually I didn't read that very carefully, did I? It says some whole numbers are not rational numbers. Well, we know all the whole numbers are rational numbers, so this is false. And once again, there was the quantifier. Each rational number is a positive number. We know that's false. There are negative numbers in the rational numbers, so this is patently false.